Welcome to Parasitology. Today, we're going to explore a topic that completely flips our understanding of nature. When we think of parasites, we usually imagine tiny, spineless creatures like mosquitoes or ticks. But what if I told you that complex animals with backbones, like birds, bats, and even sharks, can also be parasites? Let us dive into the bizarre and fascinating world of parasitic vertebrates. Now that we have introduced the idea, let us think about a walk through a dense, humid jungle. You fully expect tiny creatures like leeches or ticks to try and steal a quick meal from you. We are all very familiar with these microscopic or spineless pests. But imagine if a furry mammal or a fish did the exact same thing. Instead of tiny insects, we are looking at animals with spinal columns that have evolved to act just like giant mosquitoes. It shows us that the parasitic lifestyle is so incredibly successful that even highly evolved, complex animals have adopted it to survive. Building on that intuition, let us formally define what a parasitic vertebrate actually is. In biological terms, it is an animal possessing a spinal column that derives its nutrition at the expense of another living organism, which we call the host. The crucial distinction here is that they usually do not kill the host immediately. Unlike apex predators that kill their prey outright, these vertebrates act as micropredators. They take only small amounts of tissue, blood, or resources. This ensures the host survives the encounter, allowing the parasite to return and feed on them again in the future. Knowing the definition, let us look at some incredible real-world examples, starting underwater. First, we have the cookie-cutter shark. This is a small, deep-water shark that attaches itself to much larger marine mammals. It literally spins its body to gouge out perfectly round plugs of flesh, leaving a cookie-shaped wound. Second, we have the candiru. This is a tiny, translucent catfish found in the Amazon River. It swims directly into the gills of larger fish to feed on their blood. Both of these aquatic vertebrates perfectly demonstrate how specialized physical traits allow them to exploit much larger hosts. Moving from the water to the air, let us examine two fascinating flying examples. On the Galapagos Islands, the hood mockingbird has evolved a very dark survival strategy. When fresh water and food are scarce, it pecks at the existing wounds of larger seabirds to drink their blood. Then we have the most famous example, the vampire bat. It is the only mammal in the world whose diet consists entirely of blood. It sneaks up on sleeping mammals or birds using razor-sharp teeth to make a tiny cut and anticoagulant saliva to keep the blood flowing while it feeds. Having seen these bizarre examples, you might wonder why we study them. Understanding parasitic vertebrates is incredibly important for both evolutionary biology and practical medicine. Evolutionarily, they show us how extreme environmental pressures force complex animals into highly specialized diets. In the real world, they have massive economic impacts. For instance, vampire bats are major vectors for the rabies virus, causing millions of dollars in losses to the Latin American cattle industry every year. But there is a silver lining. Studying the anticoagulant proteins in vampire bat saliva has led to life-saving medical drugs like Draculin, which helps treat human stroke patients by safely breaking down blood clots. To truly understand the physical toll these creatures take, we must look at the mathematics of parasitism. Biologists use the blood and tissue depletion model to quantify the damage. Here is the first part of that model, which calculates the total volume of tissue or blood removed. The formula is V total equals N times VP times T. Let us break down the symbols. V total is the total volume removed, measured in milliliters or cubic centimeters. N is the number of parasites attacking at once. The variable VP is the volume consumed by a single parasite in one feeding session. Finally, T is the number of feeding days. Physically, if the number of parasites increases, the total volume lost increases proportionally, putting the host at greater risk. Now that we know how much total volume is lost, we need to understand how severe that loss is for the host. A mouse losing 10 milliliters is fatal, but a cow losing 10 milliliters is nothing. This brings us to the percentage depletion model. The formula is P equals V total divided by the product of MH and K, all multiplied by 100. Here, P is the percentage of the host's total blood or tissue that has been lost. V total is the volume we just learned to calculate. MH is the host's total body mass in kilograms. The constant K represents the average volume of vulnerable tissue per kilogram of the host's mass. If the host mass is very small, the percentage P becomes dangerously high. Let us apply our first formula to a real-world scenario. Imagine a small herd of 5 vampire bats feeding on a sleeping cow every night for 4 days. Each bat consumes 25 milliliters of blood per night. We are asked to find the total volume of blood removed. We choose the total volume formula because it accounts for multiple parasites over multiple days. We substitute 5 for the number of bats, 25 for the volume each bat eats, and 4 for the days. Multiplying 5 by 25 gives 125. Multiplying that by 4 gives us our final answer. The bats have collectively consumed exactly 500 milliliters of the cow's blood over the 4 days. We just found that the bats drank 500 milliliters of blood. Now, we must determine if the cow is in medical danger. The cow has a mass of 400 kilograms, and the blood constant is 70 milliliters per kilogram. We use the percentage formula to compare the lost blood to the cow's massive size. We plug 500 into the numerator. In the denominator, we multiply the 400 kilogram mass by the constant 70, which gives a total blood volume of 28,000 milliliters. Dividing 500 by 28,000 and multiplying by 100 gives us exactly 1.78%. Physically, this means the cow lost less than 2% of its blood. It will easily survive and regenerate the lost blood without severe health issues. Let us look at a much more aggressive example. A pod of 12 cookie-cutter sharks attacks a young dolphin. Each shark gouges out a plug of flesh with a volume of 40 cubic centimeters in a single coordinated attack. We need to calculate the total volume of flesh removed. We use the exact same logical steps as the previous example, but applied to tissue instead of blood. We substitute 12 for the number of sharks, 40 for the volume taken by each shark, and 1 for the time variable, since this is a single event. Multiplying these together gives us 480. The sharks have collectively removed 480 cubic centimeters of flesh from the dolphin in just one brief attack. 480 cubic centimeters is a significant amount of tissue damage. To understand how life-threatening this is, we must compare it to the young dolphin's mass of 50 kilograms. The tissue constant here is 30 cubic centimeters per kilogram. We place 480 directly into the numerator of our percentage formula. In the denominator, we multiply 50 by 30, giving a total vulnerable tissue volume of 1,500 cubic centimeters. Dividing the lost tissue by the total available tissue and multiplying by 100 gives us 32%. This means the young dolphin has lost nearly a third of its vulnerable surface tissue. Unlike the cow, this host has suffered massive, potentially lethal damage, showing that vertebrate parasitism can border on lethal predation. Having calculated those percentages, let us visualize this relationship on a graph. Here, we are looking at a curve showing host body mass on the horizontal axis, measured in kilograms, and the percentage of blood or tissue lost on the vertical axis. Notice the shape of the red line. It is an exponential decay curve. On the far left, where the host mass is small, the percentage of damage shoots up dramatically. This is where our dolphin attacked by cookie-cutter sharks sits. As we move to the right, the host mass increases and the curve flattens out close to zero. This is where our massive cow fed on by vampire bats is located. This diagram clearly teaches us that smaller hosts suffer exponentially higher damage percentages, which is exactly why parasitic vertebrates usually target hosts much larger than themselves. We have covered a lot of ground today, so let us summarize the most important ideas. First, we learned that parasitism is not just for tiny bugs or worms. Complex animals with backbones have evolved highly specialized traits to live this lifestyle. Second, these creatures act as micropredators. They steal nutrients like blood or tissue without immediately killing their larger hosts. Third, through our mathematical models, we proved that the survival of the host depends heavily on its body mass relative to the amount of nutrients stolen. Finally, studying these bizarre animals is not just a biological curiosity. It provides vital insights into evolutionary biology and has even led to life-saving human medicines. You now have a solid understanding of parasitic vertebrates.